Hard drives are devices that store data using magnetism. They can store huge amounts of information in a small space, but they are also prone to failure and data loss. In this section, we will explain how hard drives work and why they are not reliable. A hard drive consists of one or more spinning platters with a thin magnetic coating. The platters rotate at high speeds, typically between 5,400 and 7,200 revolutions per minute, RPM. A read/write head moves over the platter, reading or writing data as tiny areas of magnetic north or south on the coating. These areas represent the binary digits 0 and 1, which are the basic units of information in a computer. The read/write head is attached to an actuator arm that can move across the platter very quickly and precisely. The actuator arm is controlled by a servo motor that receives signals from a controller circuit. The controller circuit also communicates with the computer's motherboard via an interface cable, such as IDE or SATA. The interface cable transfers data between the hard drive and the computer's memory, RAM. To access data on a hard drive, the computer sends a request to the controller circuit, which then moves the actuator arm to the correct position on the platter. The read/write head then reads or writes the data from or to the magnetic coating. The data is then transferred to or from the computer's memory via the interface cable. This process sounds simple, but it involves many complex and delicate components that can fail or malfunction for various reasons. Some of the common causes of hard drive failure and data loss are mechanical failure. The moving parts of a hard drive can wear out over time, especially if they are exposed to heat, dust, vibration, or shock. For example, the spindle motor that spins the platters can seize up, the actuator arm can break off, or the read/write head can crash into the platter and damage the magnetic coating. Mechanical failure can result in clicking noises, slow performance, or complete data loss. Logical failure, the data on a hard drive can become corrupted or inaccessible due to software errors, viruses, malware, power surges, human errors, or accidental deletion. For example, the file system that organizes the data on the platter can become damaged, the partition table that defines the boundaries of different sections of the drive can become lost, or the master boot record that tells the computer how to start up can become overwritten. Logical failure can result in error messages, missing files, or boot problems. Environmental failure, the environment where a hard drive is stored or used can affect its performance and lifespan. For example, high temperatures can cause thermal expansion and contraction of the components, humidity can cause rust and corrosion of the metal parts, water or fire can cause short circuits and melting of the plastic parts, and magnetic fields can erase or alter the data on the platter. Environmental failure can result in partial or total data loss. As you can see, hard drives are not very reliable devices for storing data. They have many moving parts that can break down, they are sensitive to physical and logical damage, and they are vulnerable to environmental hazards. That's why hard drives will become extinct by 2027, because there are better alternatives that are faster, safer, and more efficient. In this section, we will explore how emerging technologies such as DNA storage and quantum memory could revolutionize data storage in the future. These technologies promise to overcome the limitations of traditional magnetic hard drives, which take up lots of space and have to be replaced over time. DNA storage is a technique that uses the molecules of life to encode digital information. DNA is composed of 4 chemical units called bases: adenine, cytosine, guanine, and thymine. These bases can be arranged in different sequences to represent binary code, the language of computers. For example, a 0 could be represented by adenine or cytosine and a 1 by guanine or thymine. DNA storage has several advantages over conventional storage media. It is extremely compact, every movie ever made could fit inside a volume smaller than a sugar cube. It is also very durable, DNA can last for thousands of years without degradation. One of the challenges of DNA storage is how to write and read the data efficiently. Scientists have developed various methods to synthesize and sequence DNA strands, but they are still slow and expensive compared to magnetic hard drives. However, a recent breakthrough by researchers in Atlanta, US, could change that. They have developed a chip that can grow unique strands of DNA one base at a time. The chip has multiple microwells, allowing several DNA strands to be synthesized in parallel. This could improve the speed and capacity of DNA storage by a factor of 100. The researchers hope to use their chip to store large amounts of data in DNA form in the near future. Quantum memory is another emerging technology that could transform data storage in the future. Quantum memory is a device that can store and retrieve quantum information, which is encoded in quantum bits or qubits. Qubits are physical systems that can exist in two states at once, such as an electron's spin or a photon's polarization. This allows them to represent more information than classical bits, which can only be either 0 or 1. Quantum memory has the potential to enable quantum computing, which is a new paradigm of computing that exploits the strange properties of quantum physics to perform complex calculations faster than classical computers. However, quantum memory also faces many challenges. One of them is how to preserve the quantum states of qubits without losing or corrupting them due to noise or interference from the environment. This is known as decoherence, and it limits the lifetime and reliability of quantum memory. Another challenge is how to transfer and manipulate quantum information between different qubits or devices without destroying it. This requires special techniques such as quantum teleportation or entanglement swapping. Scientists are working on various solutions to overcome these challenges. For example, some researchers are using hard drives made of DNA to store qubits. DNA has the advantage of being stable and compatible with biological systems, which could enable new applications such as quantum biotechnology or medicine. Other researchers are using optical fibers or crystals to store qubits as photons. Photons have the advantage of being fast and easy to manipulate with lasers or mirrors. In conclusion, DNA storage and quantum memory are two promising technologies that could revolutionize data storage in the future. They offer advantages such as high density, long durability, and quantum computing capabilities over traditional magnetic hard drives. However, they also face challenges such as writing and reading speed, decoherence, and interconnectivity. Scientists are working hard to overcome these challenges and make these technologies more accessible and practical for everyday use.